right, so we have been talking about the laws of thermodynamics, and last week we learned about the first law of thermodynamics, and we said that the first law of thermodynamics is essentially a law of the conservation of energy applied to heat or thermal energy. So let's just consider this closed system. The closed system consists of hot food. Oyster is hot relative to the bed of ice it's on. So you have cold ice and hot food. So according to what we've been learning so far, and first law of thermodynamics, in which direction will heat or energy flow in this case? Hot to cold, right? It's always hot to cold. So energy transfer is always from hot to cold. So the oysters will lose energy. Whatever energy they lose will go into the ice. We are considering, again, a closed system so that the interaction is just between the oysters and the ice. And so as a result of the energy transfer, will the oyster heat up or cool down? Cool down, right? If so energy goes from hot to cold, whoever is losing energy will cool down. So the oysters will cool down, the ice will heat up. Yeah, so the food will cool down, the ice will heat up. In that process of energy transfer, is energy conserved? Yes, right, because we considered it's a closed system. So none of the energy lost by the oyster goes outside of the system, and it only goes into the ice. So in this case, energy is conserved. Whatever energy the oyster loses is the same amount of energy that the ice gains, right? And this is quite intuitive. We've known also by experience that heat goes from hot to cold. Now please indulge me in a thought experiment, and let's just say that energy can transfer from cold to hot, in which case the ice will lose energy and the oyster will gain energy. And so as a result of this energy transfer, energy leaving the ice and energy entering the oyster, will the food heat up or cool down? Heat up, right? Because whoever gains energy will heat up, and whoever loses energy will cool down. So the oyster will still heat up, and the ice will cool down. So the ice will become colder and the oyster will become hotter. Is energy conserved in this case? Yes, right? We're still considering a closed system so that the interaction just occurs between the ice and the oyster, and whatever energy is lost by the ice is absorbed by the oyster. So in this case, energy is still conserved, even if energy goes from the cold ice to the hot oyster. But do we see this occurring spontaneously? I mean, in real life, can we put a pot of water on a bed of ice and observe the water boiling after some point if it's a closed system? When we say spontaneously, it occurs without any work input or without doing anything else. And it doesn't, right? We do not observe energy transferring from cold to hot spontaneously, even though energy is conserved in the second scenario. In the thought experiment that we did, energy is still conserved because whatever energy the ice lost is the same amount of energy that the oyster gained. But we never see this happening spontaneously without any input of work. We cannot cook food by putting it on a bed of ice, in other words. So this tells us that the first law of thermodynamics, which is a law of energy conservation, is not enough. Because in this case, energy is conserved, but we don't observe this happening. And so a new law is needed to explain this irreversibility. Irreversibility, what we mean is that the energy only flows from hot to cold and not the other way around. Energy is not observed to flow from cold to hot. Okay. So the first law of thermodynamics is not sufficient. And the new law that's needed to explain this irreversibility is the second law of thermodynamics. The second law of thermodynamics is quite broad, but the essence of it is it's a statement about which processes occur in nature and which processes do not occur spontaneously in nature. So it's quite hard to, the second law of thermodynamics is not very specific in the way that you can state it as just one sentence, but the essence of it is specific in which anything that you observe to occur spontaneously in nature can be explained by the second law of thermodynamics. And one way, so second law of thermodynamics can be stated in various ways, and one way of stating it is that heat flows spontaneously from a hot object to a cold object, and heat will not flow spontaneously from a cold object to a hot object. So this is one statement of the second law of thermodynamics. Again, it's not a specific statement. So if, for example, in the test, hypothetically, if we ask you to state the second law of thermodynamics, there can be many answers to that question, right? And as we do our lectures this week, you will see other ways of stating the second law of thermodynamics. And before we proceed further, let me just prepare my demonstration here. So I have here cold ice, right? So I want to demonstrate second law of thermodynamics. Heat flows from hot to cold, so I'll need cold ice water essentially at 0 degrees Celsius there. And then I have boiling water, hopefully close to 100 degrees. Okay, so cold, hot. Right, this is, it's called a Peltier device. If I put them across here so that there's a temperature gradient, might take some time. Should have prepared that earlier. But yeah, the second law of thermodynamics is telling us this is hot water in this cup, cold water in this cup. Heat will flow spontaneously from hot to cold. So at the moment, there's heat. This is just aluminum, but it's still conducting. It's not as conducting as steel, but heat is being conducted from this side, hot side of the Peltier device, to the cold side of the Peltier device, and hopefully, maybe we need some push. Need some more time. Just leave it there for a moment. Come on. Oh. Sometimes it needs to be given a push. This is also what works in your laptop, right? You have heat flowing from one side of the Peltier device, hot side, going to the cold side. And as a result, you see this fan working. So this demonstrates that as a result of heat flowing from a high temperature to a low temperature object, the thermal energy can be converted to some mechanical work.
Generally, you can generate electricity from every available temperature differential. Propeller will start.
All right. So this tells you that essentially, if you have a temperature difference, temperature gradient, hot and cold, you can generate electricity, and the generated electricity causes this mechanical work that causes the fan to spin. This is a Peltier device, which is the same fan that's in the laptops that cools down the laptops. You have a cold sink. If your laptop becomes hot, you have this energy transfer from your hot device, hot circuit, to the cold sink that activates the fan that then cools down your device. All right. And this mechanism of heat transferring from cold to hot and therefore generating mechanical work is how heat engines work. A heat engine is any device that changes thermal energy into mechanical work. All right. Yeah. So mechanical energy can be obtained just like so. And an example of an engine is the Stirling engine, which uses the expansion of the gas. We do have a Stirling engine, but this morning it was grumpy, didn't want to work. We'll see if that works. I'll bring it tomorrow. But essentially, you have a gas compartment here. If we heat up the gas expands. The expanding gas pushes this piston, and as a result, some cold air escapes in this part of the engine that contracts the work piston, which then pulls this flywheel, and the process repeats so that the flywheel rotates continuously as long as you have heat flow in here, heating up the gas, causing it to expand, and the cold gas contracting in this part of the cold sink. Right. So that's the key idea behind how engines work. You need a heat source and a cold sink. The temperature gradient is what creates the mechanical work, just like what we have here. Right, so we often draw this schematic diagram to represent a heat engine. You always need to have a high temperature source, a reservoir of heat that's at a high temperature, TH. Okay. You always need to have a cold sink that is at a lower temperature. Okay, as we've seen, heat will flow from the hot source to the cold sink, right? So the heat engine draws up energy from the hot source, and as a result, mechanical work is done. As some of the heat is converted to mechanical work, but some of the heat is expelled into the cold sink. So you have this energy QL that's expelled to the sink. Okay. So this is a schematic diagram of every heat engine. You have energy QH coming from the hot source. Mechanical work W is done, but some of the energy QL is expelled to the low temperature or cold sink. Essentially, second law of thermodynamics at work here, but second law of thermodynamics should not violate the first law or conservation of energy, right? So conservation of energy still is valid every time. And so if you see here, the input to your heat engine is the energy input from the source QH. That should be equal to the energy output out of your heat engine. So your energy output consists of work, the work done W, and the energy that's expelled QL. I'll leave it there for a minute. And hence you have the relationship between the energy drawn from the hot source QH is equal to the work, mechanical work done, plus the energy expelled to the cold sink QL. And we take all signs to be positive so that we have this conservation of energy. W plus QL should add up to be equal to QH. All right, still okay so far, right? Okay, if we wanted to find the efficiency of the engines, so when we say efficiency, it's always the ratio of output to input, right? How efficient something is a measure of how good its output is compared to the input that's put inside. So if applied to the heat engine with QH, W, and QL, right? The output, the input to the heat engine is QH. Okay, that's the energy input, the energy that the heat engine draws from the high temperature source, and the output is the work done. Right? Because what we want is the heat engine getting energy from the hot source, converting that to work. So the output we are after is the work done, but there's some energy expelled as heat waste to the cold sink. But when getting the efficiency, we're just after the output. The output in that case is the work done. The input is the how much energy is drawn from the heat source. In other words, the efficiency is work divided by QH. Okay. But we can also use the conservation of energy, the expression for conservation of energy from the previous slide, which relates the energy from the hot source is equal to work plus the energy expelled to the cold sink. We can use this to replace work so that our expression for efficiency just involves the energies in the hot and cold source, hot source and cold sink. Hence you have this efficiency is also equal to like this, QH minus QL over QH. And or you can simplify that because QH can be distributed to each term. So you can simplify this. QH divided by QH gives you 1 minus QL divided by QH. So your efficiency can also be written as 1 minus QL over QH. And written in this form, okay, when will we have an efficiency of 100%? So efficiency is equal to 1 minus QL over QH. When will we have a 100% efficiency?
No, sir.
Yeah, QL equals 0, right? Because then if QL equals 0, this whole QL over QH is equal to 0. And QL equals 0 means that there is no heat waste, right? Meaning no heat is given off to the sink, and all of the heat drawn from the source is converted to work. But this is impossible, right? And right, this is impossible. We can only observe this in real life, right? The any device you have heats up. Your cell phone heats up, right? The hood of your car heats up. If you put your hand at the back of the refrigerator, you feel that the back is hot. In other words, any device will have some heat waste. There's always some energy expelled, and work is never 100%, right? The energy drawn from the source is never 100%. Okay, so it's impossible to have 100% efficiency. And since the second law of thermodynamics is a statement about which processes occur in nature and which do not, we can also state the second law of thermodynamics as a heat engine cannot be 100% efficient, because it's impossible to have a 100% efficient heat engine. And second law of thermodynamics is a statement of what's impossible and what's possible in nature. Right? right? So as I've said, no engine can completely transform any given amount of heat into work. Okay? If a salesman comes to your door claiming that this device is 100% efficient, then you know that that's a hoax, right? The second law of thermodynamics tells you this is impossible. 100% device is impossible. There will always be heat that's going to be expelled in any engine, in any device. Okay. Right. And because you cannot have 100% efficiency, the second law of thermodynamics also limits the efficiency of any heat engine. Cool. Right. Any questions so far? So that's essentially the essence of the second law of thermodynamics. As I said, you can state it in any way, in any possible way, as long as it's sensible, of course. Yeah, you cannot have 100% heat engine, or any device needs to expel heat, or hot food will always lose energy to cold food, right? Any of those ways of stating second law of thermodynamics is valid, and they should be considered correct if you're asked such questions in the test or assignment or anywhere. Okay, so let's look at some examples now. Here, what is the efficiency of the heat engine shown below? So here, the schematic diagram of a heat engine will always show a hot source, high temperature source, and it will always show a cold sink. Okay. Right, and you have here their joules, measured in joules, so that means you have here numbers given as energies. You're given energies, and you want to find the efficiency of this heat engine. Did you get why it's 60%? Right? Okay, efficiency, it's defined. The basic definition of efficiency is output over input. Your heat engine draws energy from the hot source. So this will be the input, the amount of energy drawn by your heat engine from the hot source will be the input energy. Your heat engine will do work. Right, your heat engine will do work. So your output, the output you want out of your heat engine will be the work done. Right, that's the work done. Okay, and this 200 joules, this is the energy expelled to the cold sink. Right, you see the arrow there, energy going to the cold sink. This is the heat waste. Right, it's not the output, but it's the wastage, how much heat was not used up in doing the work. And so when you calculate for the efficiency, this is the output 300 joules divided by the input 500 joules. Right, and that gives you 60%. Cool. Right, relatively simple. I hope so. So I hope this week's topics are a bit lighter than they are. So it's a good way to end the semester. Right, so try these exercise questions. You have an automobile engine which has an efficiency of 20%. It produces an average of 23,000 joules of mechanical work per second. Right, so you're given the output of the engine because you have joules per second or 23,000 watts. How much heat input is required to have this efficiency and how much heat is discharged as waste from this engine per second. Yeah, I've written down relevant heat engine equations on the screen in case you forgot to take notes earlier. Okay, let's look at the solutions to this. So what we have here is the efficiency. Okay. Efficiency is 20%, or we can also write as 0.2. Right, 20 divided by 100 will give you 0.2. And the average mechanical work is 23,000 joules per second, or 23,000 watts. Okay. Right, what relates the work to the efficiency is the definition efficiency, output over input. The output is the work done, and the input is the QH. It's the heat that you get from the hot source. Hence, your heat input from the hot source will be the work done divided by the efficiency, or you have 23,000 joules per second divided by 0.2. So every second, 115,000 joules of energy is drawn from the hot source. And as a result, work is done. 23,000 joules of work is done every second, giving an efficiency of 20%. Okay. Right, no heat engine is 100% efficient, so some heat needs to be discharged as heat waste to the cold sink, and we want to find how much heat is discharged as waste, meaning we want to find QL. Right. How much heat in joules per second how much heat is how much joules of heat is expelled every second by the heat engine. We know that energy needs to be conserved, so whatever input, so input should be equal to the output, output plus the waste. Okay. So whatever energy is drawn from the heat source will go into work plus the heat that's expelled, QL. Right, so QL, the heat waste, is what we're after. And so you have energy drawn from the hot source, 23,000 joules every second is drawn, minus the work that's done every second. Oh, did I? Yeah. It's the other way around. Yeah, it's 115,000 joules of heat from the source and 23,000 joules of work every second. Okay, you can subtract this because you have the same units. So that's 93 or 92,000 joules is expelled as waste every second. All right, easy peasy. Oh, definitely much simpler than doing the integral to find the work in first law of thermodynamics. Right, any questions about the exercise or the second law of thermodynamics? Right, good. Okay, so as I said, hopefully this week is going to be an easy week to wrap up the semester, and that wraps up second law of thermodynamics. It can be stated in various ways. These are just two examples of how to state the second law of thermodynamics. You can come up with other ways as long as it doesn't violate what you observe, what's not possible and what's possible in nature. We applied it to heat engines, finding the efficiency of the heat engine and doing conservation of energy in heat engines. Tomorrow, we will look at an ideal heat engine called the Carnot engine and look at the third law of thermodynamics. But I wish you a good day today, and I'll see you in the lecture tomorrow.